So this is a fairly easy to understand cryptosystem, which I believe is fairly secure. So what it does is it reads each row as a binary integer, and then it's going to replace that row with another binary integer depending upon the key. So the key is a row permutation of 8 elements, 8 different positions. There are 256 factorial choices for the row permutation. So it's going to apply that row by row, and then it's going to apply the column permutation column by column. And this is going to diffuse the information. So when this row is encrypted, when we finally get to the columns, it's going to affect how all of the columns are encrypted. And then when we go back to encrypt rows again, the column encryption will also be diffused. So each bit is going to affect all the other bits fairly quickly in this system. So we do a row sweep, then we do a column sweep, then we do a row sweep and column sweep. So you can choose whatever number of rounds. You might want to set this to maybe 64 rounds, one for each bit. You could keep that set, and if you accept that as understood in the system, then the key is just 2 different permutations, the row permutation and the column permutation. And once you have those, it's really easy to calculate the inverse. And when you decrypt, you just do in reverse order what you did to encrypt. So to a single round is I'm going to read row by row. I'm going to replace this binary integer with the one indicated by the key, and that's represented as an array of integers of length 256. So I'm going to row by row replace the row with a new integer depending upon the key, and then to complete the round I'm going to do the same thing with the columns using the column permutation. So that would be 1 round of encryption. And then to decode, I would undo the columns. Since I did the columns last, I need to decrypt them first. I'll use the inverse permutation for the columns, and then I'll use the inverse permutation for the rows. Now you probably would want to use many rounds on this system, so you're really going to get an intensely transformed grid, because the message here is the entire grid or square of 64 bits. So this system is designed to send 64 bits at a time, and it does preserve the 2-dimensional relationship of the bits. So if this was a game of Go or something, you could encrypt anything that you would represent with a grid of 64 bits. So how many keys are there? If you have a fixed number of rounds, say 64, you just need to choose one of 256 factorial possible row permutations and one of 256 factorial possible column permutations. So the key space, there are 256 factorial squared possible keys. And that is a massive number. So basically, if someone were to brute force this, they might try every combination of row permutations and column permutations and see if when they decrypted it 64 rounds, assuming that's public information, they would see if there's any information to be had that way. Like if they were to try this random key and then decrypt, and then they find something that looks like an encoded English language message, they might say, okay, this is probably what was sent. But since there are so many possible keys, that would be computationally too intensive, right? They would need incredible good luck or incredibly powerful computers to do that. So this concept is a very simple concept. It would be pretty easy to extend it to 64 by 64 bits. The thing that takes the most space is nothing takes a lot of space, right? You have to create the permutation, which is pretty simple to do. There's a shuffle algorithm. First you create a vector that's 0, 1, 2, 3, 4, right? And then you want to shuffle that. And that'd be your key for the rows, and you'd do the same thing, and you would generate a random column permutation. So there's no there's no intense memory storage. You only have to store the current state of the grid. You'll probably want to store an inverse row and column permutation, but again, this is really not memory intensive at all. So it's a very simple algorithm that could be easily extended if you wanted larger grids. I just chose this 8x8 because it was pretty simple to do, and it's big enough you can imagine sending 64 bits that are meaningful. You could imagine that maybe in some military situation, in crypto books you'll see like attack the bridge at dawn, that sort of thing. But also, since you're encrypting a grid, this would be an interesting way to encrypt two-dimensional information. A bigger part of this, a bigger version of this system, you could encrypt a real primitive bitmap, where 1 indicates a black pixel and 0 indicates a white pixel. So I can imagine you could encrypt pictures if you wanted to. Very simple, monochrome, not grayscale. I mean, literally just zeros and ones. Of course, as you watch this go, you can also think of this as a reversible cellular automaton. So unlike the game of life, which is not reversible, you really can, go 1,000 steps into the future and then reverse the whole thing, rewind. You could do alternate realities where you flip one bit, follow that alternative reality again, rewind. So this to me wasn't really about making something that's useful, though that maybe it could be used. It's more an attempt to make a symmetric crypto system as a work of art. So I wanted it to be very simple to understand. Probably someone's done something like this before, because these are some fairly basic concepts. But if nothing else, I think this illustrates some of the basic concepts of cryptography in what I hope is an effective way.